Welcome back to the video series. Today we'll be doing two-factor fully between analysis of variance. I do want to indicate that there are two other types of two-factor analysis of variances that we will not be covering. One would be the fully within groups and the other would be the mixed model. So let me introduce you a little bit to the types of variables that we have here, and then I will talk about what it would mean to if we were doing a video on the other types of ANOVAs, exactly what we'd be looking at in this. So for this particular example that we're using, I'm drawing from research that was done in 2006, and really there's two variables of interest that we're looking in. So there's two independent variables. We will still, of course, just have the one dependent variable that we're interested in. So the final dependent variable is how well do they do on a final retention test or a final test, if you will. The two independent variables, or the two factors that we are interested in, is there's a question of whether or not how long they have to remember the information will affect their ability to recover the information. So if I give them the final test 5 minutes after their final study session, where there'll be a difference on that in terms of their final retention, their final ability to recall the information, versus if I test them a week later after their final testing period. Sorry, their final study period. Likewise, I'm also looking at the type of studying that they're doing. So again, I have retention duration, how long do I wait before I test them, and then what type of study will the individuals be engaged in. So I have three different types of study, and the question that we're really looking at here is whether study in and of itself is sufficient, or if there is some benefit to self-testing or self-examination before the final test. So when I refer to the self-testing or the self-examination, that is a type of study and it is not the final testing phase. So to help you understand it, for this group here, the type of studying that they do is they have 4 study sessions, and during the study sessions they're literally just doing that. They're just studying the information. Whereas another group, they also have 4 study sessions. 3 of them, are indicated by the S's, are just as the previous group that we talked about. Those are just study sessions, but prior to that final testing phase, they're actually going to do a self-test. So they're going to test the material, test their knowledge of the material prior to that actual final examination, if you will, or the final testing phase. The last group of individuals, they study the material in the traditional sense only once. The remaining 3 study phases for these individuals are self-examination or self-testing. So the question is repeated testing beneficial towards encoding when it comes to that final test period? So we are doing a fully between analysis of variance. What does that mean? That means the individuals in this condition, where they study the material 4 times and then their final test comes 5 minutes after their final test phase, those individuals in that group or that cell that we're talking about here are completely different than the individuals that engage in this type of study and testing and these individuals that engage in this type of study and testing. So each cell, each condition, is different individuals. We have no individuals that are doing multiple things. It would be possible to do this design with fully within. What do I mean by that? Imagine we have 10 individuals. What I do is I give them a block of material. Let's say they're studying 100 items. Those individuals study those 100 items 4 times, just as indicated by this, and then we test them immediately after, 5 minutes after, the short testing retention phase. And so then we see what their score are. But then those same 10 individuals are given another 100 items, and then they're asked to study 3 times and give themselves one self-examination. 5 minutes later, they're given the final exam. Then that same individual would do another 100 items with 1 study phase, 3 testing. Likewise, they would also be doing this where they study it another 100 items 4 times, but wait 1 week. That would be considered fully within or a fully repeated measures design, because I have one group of individuals that's engaged in each of the 6 possible conditions. It might also be a mixed model. A mixed model would be something where we would have one repeated condition, but then a between groups condition. So for example, I might have 10 individuals doing the 4 study 5 minute, the 3 study 1 testing 5 minute, and then the 1 study 3 tests 5 minute delay, but a different group of 10 individuals doing the same thing, 4 study sessions, 3 study 1 test, 1 study 3 tests, but for them, they have to wait the 1 week before they're tested. There's different reasons why you might engage in a fully between versus a fully within versus a mixed model. If I have fully between, if you recall from previous videos, I'm always adding noise because I have different individuals in each group. There's going to be those individual differences that is going to add to the overall noise because I expect different performances from different individuals. However, the problem with fully within is even though I get rid of the between individuals variance, that noise, and I'm restricting myself to the same group of individuals, so their performance should be roughly the same, and so I reduce that amount of variance, I do get into other problems such as perhaps practice effects. As they do this multiple times, they just simply get better at the overall process of studying and recalling information. So once I introduce a practice effect confound, I am no longer confident that the results that I see are necessarily because of retention duration or encoding type, but it could also be the practice effects. Why might I want to do a mixed model? Well, imagine that I do have this encoding type. I've got the 3 different types of encoding situations, but imagine instead of retention duration, I'm instead looking at males versus females. Even though I could have the males do the 4 study, then also do a different group of words and do the 3 study and 1 test, and then likewise a different group of words, 1 study and 3 test, I can have the males do that as a repeated variable. It is rather difficult experimentally to then spontaneously convert our males into females and also have them do the other condition to be a fully repeated design. So in that case, it just makes sense I have to have a mixed model. One of those variables, the males versus females, kind of has to be a between groups variable. The other one can be repeated. So there's a number of different reasons for approaching different ones. The computations are very similar with, again, some differences obviously. The only one that we will be doing for this video series is that fully between, again, indicating that each cell here, each group, or each connection of the 2 variables is an independent or a unique group of individuals. So the data that I'm using for this is not drawn directly from the 2006 journal article. I've made up data that meets our needs fairly good here, but the final results very closely mirror or match what we saw in the 2006 article. So as we move forward, you're going to have an easy ANOVA table, just as I provided you with before. This video is going to have a bit fewer of the colored boxes because the assumption is that you've spent some time on the previous videos. You're kind of starting to get a handle on the computations that you're dealing with. However, on the easy ANOVA table, one thing that I really encourage you to do is kind of commit to memory some of the hints that I've given you here. You'll notice we'll be computing between treatments. And when we're doing this, we'll be dealing with the cells. Then when we go to factor A, we'll be doing rows. Then factor B will be columns. Then when we get to the error term, we'll be going back to cells. It doesn't matter if you do rows then columns or columns then rows, as long as you are consistent. So I'm presenting it this way, and if you just commit to memory cells, rows, columns, cells, then that will help you avoid some potential errors. The other thing that I want to point out on the 2-factor ANOVA table is, again, I have some of the terms indented and some are all the way back. So for example, I have between treatments and the error terms all the way back, but then I have this indentation of factor A, factor B, and the A by B interaction. As we had on previous easy ANOVA tables, that is because these are a subdivision of between treatments, or another way of saying that, I get my overall between treatments, but then I divide that into the individual subcomponents, A, B, and the interaction. So I'm taking the overall thing, I'm chopping it into pieces, and then I'm indenting that so that you know that these are subsections of it so you don't end up doubling up on some of the information, as was a risk on the repeated measures ANOVA that we looked at before. The formulas that we see here are very much the same as the formulas that we saw on previous easy ANOVA tables, or even as we go back to z-test or z-test. So for the example, the first formula, I'm just asking to subtract an individual mean from the grand mean, square that and multiply by n. Same thing for factor A and factor B. I'm just using, instead of the x variables, I'm using the A variable or the B variable. The computations are identical. So if you've taken the time early on in the video series to get your strong understanding of that simple computation, then the logic ends up sticking around for the rest of the video series. So let's move forward and start breaking this down. Here is our data. Just as before, as we had with the orange boxes, I have the 6 cells indicating the encoding type and the duration of time that they had to wait before they were tested. So I have the 3 different types of encoding, and then I have the 5-minute and the 1-week wait times. We don't have a toolbox per se for the two-factor ANOVA because if you map it out in this way where you have the data in the cells, then what happens is the cells themselves, as well as boxes in what I call the margins, end up becoming your toolbox for you. So as long as you write this in a systematic, organized way, anytime a formula is asking for a variable, all you have to do is go to this page of information and you'll be able to pull that information readily from it. So remember, between treatments, cells, rows, columns, then back to cells. So that means I'm going to need to do some computations in each cell. I'm going to need the means for each individual cell. So you'll notice that I've done that 6 times. In order to get the mean for each cell, again, I just sum the values for that cell, divide by the number of observations for that cell. That will give me the mean. In this case, that's our x variable. So I have x bar sub 1, 1. The mean for row 1, column 1, that's that cell. Then I've got the mean for row 1, column 2. So I'm going to be calculating out those individual means for each cell. Cells, rows. Now I need to do the same thing, but I'm dealing with rows. I need to calculate my first set of marginal means, and this is going to be, again, factor A is my rows. So instead of using the x variable, we're going to the a variable. So A is just the sum of all the observations in the entire row. So if I add up all of the values in the 5-minute condition, that gives me 2,224. As you notice, I've got an n over there, n sub A1, that's 29. So if you look, I've got 8 observations, 11 observations, and then finally 10 observations. I add that together, that gives me a total of 29 observations for that row. Therefore, the row total divided by the number of observations for that row is going to give me a row marginal mean of A bar sub 1 of 76.69. I do the same thing for row 2, which is all of the 1-week observations. We'll get that marginal mean of 51.19, and then we've got cells, rows, columns. We're now going to be doing the same thing with columns. So we will be adding column 1, dividing by the appropriate number of observations in that column, and so now I get my marginal means down here for the columns. But as you recall in the formulas, we're also going to need those grand means. So over here, as I look at over here with both of them, I'm going to have the grand total of 3555. I've got a total of 55 observations. When I divide that out, I'm going to get G bar, grand mean, of 64.64. As, again, you should be fairly familiar with the previous statistics that we've done and the video's lectures. I'm not going to spend as much time in the individual slides, so what I will do with the next slide is I'm simply pulling up how we compute sum of squares between treatments. Again, sum of squares between treatments, commit to memory, cells. What does this mean? I'm doing the computation that is asked for in each cell. So if you have that committed to memory and you say to yourself, I'm doing a cells computation, simply ask, how many cells do I have? 6 cells. If I have 6 cells, then that means I will be doing this formula 6 times. So what is it asking me to do? It is asking me to take the mean for each cell, subtract the grand mean from it. Remember, order of operations, I'm doing parentheticals first, then I'll do the exponent, then finally I'll multiply by the number of observations appropriate for, in this case, cells, so it'll be the first cell. So you notice, for my first computation, I am taking the cell mean for this first cell, that's going to be 82. I'm subtracting the overall grand mean that we see down in the corner of 64.64. Once I subtract that, I'm going to square it, multiply by the number of observations in the cell that we have here, which is 8. That's going to give me 2410.96. I will then repeat that computation for each individual cell, so I've got a total of 6 computations, Once I have done that, I will then finally do my last order of operation, which is the summation. I'm going to add those down, and as you see over there, that gives me a total of 11,614.75. That is going to go into the table for SS between. But now we have to move down to sum of squares for factor A. Remember, cells, rows, so now I'm doing rows. How many times will I do that individual formula? I will do it twice because I have 2 rows. So now I'm not worried about the cells. I'm going to start looking again at my first marginal mean. The formula is asking me to take that first marginal mean, or the row mean, subtract again the grand mean, and then multiply by, after I do square it, multiply by the appropriate number of observations for that row. So my row mean is A bar 1, 76.69, minus the grand mean of 64.64, square that, multiply by the appropriate number of observations for that row, 29. That gives me 4,210.87. Now I do the same computation for the next row. Once I've done that, I will finally do my final order of operations, which is going to be summation. Add those together, I get 8914. If you've been committing this to memory, you know what's coming next. I did cells, I did rows, so now I need to do columns. So we move to factor B. We look, we've got our B bar 1, B bar 2, B bar 3. We've also plugged in our in values in each of those marginals. How many columns do I have? I have 3. I know I will be doing that equation 3 times. So now again, I've got the appropriate in, 18 for this first column. I've got the 58.66 for that first marginal mean for columns, minus that familiar grand mean that we've been seeing of 64.64. I do the math on all 3 of those, and then I add them together. I get 968.41. Cells, rows, columns, where am I at? I'm back to cells. So now what I need to do for the error term is simply, as the equation asks, compute the sum of squares in each cell. By this time, you should have done sum of squares multiple times. You should be very comfortable with it. Just to very quickly reiterate, again, I have the individual cell mean. I take each individual score, subtract that mean for the cell. Once I get the difference, in this case -2, I'm going to square it. That gives me 4. I do that for each value in that cell. I add it down. So I sum these squared deviations. I get 232. I do that for each individual cell. Just be careful that you're grabbing the mean for that cell. Work the sum of squares for all 6 cells. You know that if I'm dealing with cells, I'm going to be doing this formula 6 times before I finally add it. Once I've computed all of the sum of squares for all 6 cells, I add those together, I get 4702. I'm now in very good shape for the first bit of my Easy ANOVA table. I did the SS between. We got 11,614.75. We got 8914.33 for factor A, 968.41 for factor B. I've got to skip over down here to cells again, so this is our error term. That's the sum of squares for all 6 cells added together, 4702. Remember, between treatments, I am subdividing that. I'm chopping it into 3 components. So if I have the total and I have 2 partials, to get to that last one, all I have to do is subtract the 2 partials from the total. So you'll notice I take the total of 11,614, subtract the 8914 and the 968. That will leave me with the interaction sum of squares. Very, very simple math that we're doing there. Similarly, we need to do our degrees of freedom. I've given you the formula. Little a is the number of levels of factor A. Factor A was rows, so I'm going to have 2 levels for factor A. Little b is the number of levels of factor B. And again, all of that is notated down here on your Easy ANOVA table. Factor B was columns, so I'm going to have 3 levels or 3 columns. So that's going to be 2 times 3 is going to be 6 minus 1. Another way to do this, if you kind of get lost in the formulas at times, is again, this is another reason why memorize cells, rows, columns, cells. How many cells did I have? 6, but I'm going to lose a degree of freedom, so 6 minus 1 is 5. How many rows did I have? 2, but I'm going to lose a degree of freedom, so 2 minus 1 is 1. How many columns did I have? 3, but I'm going to lose a degree of freedom, so 3 minus 1 is 1. Then finally, to get to the interaction, if you just look here, A by B interaction, but it's also, remember, X we sometimes use for multiplication. So to get my degrees of freedom for the interaction, just simply multiply the degrees of freedom for A times the degrees of freedom for B. That's going to give you your degrees of freedom for your interaction, or in this case, 2. The final one is, again, we're back to cells. All you need to do is remember I need my total number of observations, 55, minus the number of cells that I have. So 55 minus 6 is going to give us 49. The computations here are very easy. As always, you can choose to do your computational formula to get your error term to double check, because you can also add, as before, between treatments plus error will give you that final total term. If you compute it both ways, that's a good way to check and verify if you've done your computations correctly. But moving forward, again, here we're just adding those together. Once we have our degrees of freedom calculated, just like before, all we're going to do is divide across to get our mean square. We do not need it for between treatments, but we do need it for all of the rest. We need the factor A, we need factor B, we need the interaction, and then we need that error term, because that is going to be our denominator. As with all the other ANOVA tables, our denominator is always this bottom term down here. So I just simply divide across. I've got 8914 divided by 0.33 divided by 1. That's going to be exactly the same value. Obviously, when we do the math, we're going to have to divide here by 2, divide here by 2, and then finally, we're going to divide that 4702 by 49 in order to get our mean square terms for that easy ANOVA table. So as we move forward, I've filled those in. If I've not made any mistakes in the math, then we've got those mean squared error terms, and as before, we're going to have an F value. But now, we're going to have 3 separate F values because we have 3 hypotheses that we'll need to deal with. So we're going to have the F value for factor A. So as before, we're going to simply use this value here. This is our numerator. We then have to divide by the denominator. The denominator is the same for all 3 of these. It's always going to be that bottom error term in this case. So I've got 8914.33 divided by the 95.96. Then we just move down. We're going to take that 484.21 divided by 95.96. Then finally that 866.01 divided by 95.96. Very simple division in order to get us to our final F values. We have 3 F values. Remember, for F we need the associated degrees of freedom. So if I'm looking at the F value for factor A, what's the degrees of freedom for the numerator? Well, all I have to do is go back. I've got 1. What was my denominator? Well, with all of them, it was the bottom one. It's 49. So I have F of 1, 49 equals 92.9. That's my F value for factor A. I have F of 2, 49 equals 5.05. That's my F value for factor B. Similarly, for the interaction, 9.02, I have an F of 2, 49. So we now know what the observed values are. We are going to eventually have to look up the F crit values for those, but then we also have to develop our hypotheses and what do each of these individual F values actually mean. So what is factor A? I provided you with just a portion of that easy ANOVA table, but factor A is again the rows. So when we're looking at factor A, we're not looking at the whole research question. So don't worry about all the cells and all that sort of thing. We are just looking at the rows. What were the rows again? Remember, the rows were the duration of retention, or 5 minutes versus 1 week. So when I'm looking at this, what I'm basically saying is I don't care about anything else that you did. I'm ignoring what their study sessions were. I'm just grouping them all into one big 5-minute group. And then I'm taking the rest of them and grouping into one big 1-week group. This is also often referred to as collapsing across the other variable. I'm collapsing across encoding type, study type, and I'm just dumping them into the other variable. So really what I'm doing is I'm asking the question, if I just look at the amount of time that they have to hold on to the information before being tested, is there a difference between 5 minutes and 1 week? Basically, factor A is, in this case, because I only have the 2 variables, the 2 levels, it's a t-test comparing 5 minutes with 1 week. I don't care about anything else yet. I just want to know if that's there. So, as I start building that, I need to develop a hypothesis for factor A. So I need the null and experimental for factor A, and the null experimental is basically saying their performance on that test will not be affected by how long we are asking them to remember that information. The experimental is obviously yes, their performance on that test is going to be affected by how long we ask them to maintain that information. Hopefully right now, if you've been thinking about this at all, you should be in your mind thinking, well, heck, I can remember something for 5 minutes much better than I can remember something for 1 week. Well, is that the question? That would be the anecdotal observation. There's probably research out there that backs that up, but do we actually find that with this data set? In order to answer that question, we have the F value, the F observed of 92.9, but we need that F critical value. You should have experience looking that up. Remember, in the F table, you're going to have the degrees of freedom numerator going across the top, the degrees of freedom for the denominator. So we're going to need that F value for 1,49. That value should be 4.04, so we know our critical value. We know that 92.9 falls well into that TEL, into the significant region, so we do reject the null hypothesis. Remember from the previous videos, all the F tells you is at least one mean is significantly different from at least one other mean. However, in this case, it's simple. We only have two means, so we know which means are different from each other. All we need to do now is look at the actual averages for those rows. So I've got A bar 1 and A bar 2. So basically my 5-minute group had a final test performance of 76.69. Higher scores are better here, so that means that they performed significantly better than the individuals that were asked to remember this information over the course of a week. Their score was only 51.19. So your personal anecdotal observations and the results that we get here match what's been found in previous literature. The shorter the time frame that we ask people to remember things, the better that they will do at remembering it. In a lot of the literature, this is actually referred to as the recency effect, as I've indicated in the red box. And so this is a common finding, and even though it's pretty straightforward, this verifies that our procedures, our experimental methods for this particular research that we're doing is matching well with what's been found before. So it's just a nice validation, even if it doesn't add anything new to our understanding of psychology and memory. So we move forward. What is factor B? Again, factor B, I'm not doing the entire thing right now. I'm collapsing across the other variable. So what am I retaining and what am I collapsing across? I'm collapsing across rows because I'm dealing with columns. So I am taking everybody, regardless of if you were tested after 5 minutes or 1 week, and I'm dumping them into one pool, but I am still retaining how you studied. I do still want to look at the individuals that only studied, the individuals that studied with one practice or self-examination phase, and then the individuals that had one study phase followed by 3 or repeated testing, repeated practice testing. Effectively, what I am doing with factor B is I am computing a one-way ANOVA where I am just looking at the 3 different encoding or study sessions. So I'm not concerned about retention. I just want to know, does encoding impact their ability to take that final exam? So I have that F value, but again, as always, I need to develop my hypotheses. So what are my hypotheses for factor B? The null hypothesis is test performance is not going to be affected by the type of encoding. Obviously, the experimental is that their ability to take that final test, that test performance, will be affected by how they study the information. As always, we're going to need to get that critical F value. You should be able to look that up on the table. So again, now my degrees of freedom are 2 and 49. The associated critical F value for that is 3.19. 5.05, even though it's not as robust, still falls into that critical region, indicating that we do have a significant effect of encoding type. But remember, all that tells us is that at least one of these means is significantly different from at least one other. So as before with the previous videos, as with the previous ANOVAs, you're going to have to do post hoc tests. We have 3 different means because we're dealing with 3 columns. Therefore, we're going to need to do 3 pairwise comparisons. Remember, however many means that you have, you'll do 2 plus 1. That tells you how many pairwise comparisons. So we're going to need to look at the difference between B bar 1, that first one, and both the second and the third, and then finally we'll have to look at the difference between B bar 2 and B bar 3. Because we've done this before, I've already done the math for you. I've done all of those pairwise subtractions for you. So I get a mean difference of negative 9.44, negative 8.22, and 1.22. Remember, to help you think about this, I refer to these as Tukey's post hoc observed. Why do I call them Tukey's observed? Because I've actually measured these means. I actually got these scores and then I subtracted them, so I know these comes from observed values. But with any observed, I need the critical value. So again, in terms of my classes and to help you think about it, when you compute the Tukey's HSD formula, I think about that as Tukey's HSD crit, just to help keep you on track. It's not really widely done at all in statistics, but it's a good way of relating what you're doing now with previous information. So we go back to that Tukey's HSD formula. We're going to need that Q value. Remember, Q comes from the studentized range table. We're going to need the mean square error term from the F table that we just computed, and then we're going to need the appropriate N. Remember, if you have unequal N's in the different conditions, in this case I do, I have 18, 20, and 17, I'm going to need to use that harmonic N formula to calculate the appropriate N for the formula. So I'm not going to spend time on this because we've already done that in previous videos. I've plugged in the values, so I've got 3, the number of groups that we have, the number of columns, over 1 divided by 18, 1 divided by 20, and 1 divided by 17. When I do that computation through, I get 18.18. So now I just need to work on filling out that formula. I'm going to dump the 18.18 that I just got into the denominator of that fraction. I'm going to get the MS mean square error term from my easy ANOVA table. That's 95.96. Then I need to get the Q value from the studentized range table. So remember, unlike the F table, which is asking for degrees of freedom up here, the studentized range table asks for the number of means that you're dealing with, in this case 3. So I'm going to have 3 and 49. But remember, as always, if 49 is not on the table, which it is not in this case, you want to go to the lower value. In that case, it is 40. So that is going to give us a Q value of 3.442. When I work that through, I get a critical value of plus and minus 7.91. So again, to link this with how we've made these decisions in the past, I basically have the two-tailed distribution, negative 7.91, positive 7.91. I now then take each of these mean differences and ask myself, where does it fall? Negative 9.44 is going to fall down here in this negative tail. It is in the reject region, so that means those means are significantly different. Likewise, 8.22 falls in the tail, negative 8.22, so that is significantly different. However, 1.22 falls in the fail to reject region, so I'm going to indicate that's not significant with the superscript n.s. So now we need to interpret these. What do these mean? Again, I have the mean differences between groups 1 and 2, between groups 1 and 3, but not between groups 2 and 3. So let's look at groups 2 and 3 and start with that. 2 and 3 are statistically equivalent. So even though the means are slightly different, 68.1 and 66.88, the statistics are telling us effectively that's noise. Those means are effectively equal. So what does this mean? If I test myself once, or I test myself 3 times, it doesn't seem to matter. One testing phase is sufficient in order to result in the performances that we're seeing here. So we know that these two means are statistically equal with each other, but how do they relate to the simple study phase? We know that both of these means are statistically different from mean 1, as indicated by the first 2 differences, and both of these means are higher, statistically higher, than the simple study phase. So if we ignore the retention duration, what does this tell us? At least one practice test phase, one self-examination phase, is going to result in much higher performance, or statistically significantly higher performance, than if all we do is study the information. That's what we have now in terms of this main effect. However, when you are doing a two-factor analysis of variance, if you have main effects for the a main effect for the interaction, I apologize, let me rephrase that. If your interaction is significant, then you must only interpret the main effects, the significant main effects, in relation to a significant interaction. So our interaction, the critical value again for 2,49 is 3.19. We did have an F value of 9.02, indicating that our interaction was significant. So we now must interpret those main effects in context of understanding the interaction, and because those two variables are interacting together. So we do know that there is a difference based on how long they have to remember, 5 minutes versus 1 week. We do know that there is a main effect of the type of encoding, at least initially telling us that at least one self-examination phase is beneficial. However, we have to look at the interaction because we do have that. So even though that main effect for factor B indicates that self-examination is important, it does not take into effect all of the conditions simultaneously. It only looks at that by collapsing. So we have to look at it the entire picture at once because that main effect for the interaction effect was significant. So even if we do benefit from testing, there may be more to the story and we need to understand that story. The best way to do that is to look at all these cells together. We have to develop that hypothesis for the interaction. So simply stating, encoding and testing delay do not interactively affect test performance, whereas the experimental is encoding and testing delay do interactively affect the test performance. We have already decided to reject the null, so we do know that they do interact. And really the best way usually to try to understand what's going on is to plot all of your means, your individual cell means, onto a graph so that you can look at what's going on. So I have plotted each of those individual cells. Remember, we had the main effect of retention delay. How long do you have to hold on to the information? As we look at the graph, it does, across the board, match up with that main effect. What do I mean by that? This line here, the 5-minute line, is higher across the board than the 1-week delay. So yes, it is true. Immediate retention, they are going to do better on that final exam regardless of anything else. What about the test encoding, using self-examination to help? The main effect indicated that at least one test phase was beneficial to your final performance. And if we look at the 1-week condition, that main effect holds up because in both of the conditions where there was at least one testing phase, their performance is higher than when they just studied the material. But that main effect does not hold up under the 5-minute delay. In fact, with a 5-minute delay, the best performance was when all they did was study the material and they did not actually have a self-examination phase. So the benefits of testing, self-examination, repeated testing, depends upon what type of retention duration you are being asked. So that main effect is not a law across the board. And in fact, if you know that that study, that final testing session is going to happen virtually immediately after your final study session, then that is one situation where you would actually want to not engage in self-examination practice, but just simply study and get ready to launch that information onto the test when it is provided. In pretty much every other instance, it turns out that self-examination is beneficial, and in fact, because after 5 minutes we have the peak point here, it looks like that, well, if I know that it's coming and I have to do a self-examination, one is the best situation versus multiple self-examinations. But if I'm asked to retain that information for a long period of time, then even though the results indicated for just the main effect that one test was equivalent to multiple self-examinations, when I look at this, and I would have to do more after post hoc analyses to really break this down, when I do it at the level of the interaction, I'm not still convinced at this point that one test is equal to 3 tests. However, for the purposes of this video series and for the class that this is currently linked to, we do not do the further post hoc analysis. We only do the post hoc analysis at the level of the main effects if you have 3 or 4 levels for a given main effect. So again, for what we just did, we only had to do it for factor B, the columns. However, if I had 5 minutes, 1 week, and 1 month, then at that point I would have that third level for the retention phase, and I would also have to do post hocs for that if it was significant. So in this case, we do know that yes, there is an interaction. It is not across the board that self-examination is helpful, but it depends upon the retention phase that you are looking at. We have gone through all of the computations for the two-factor analysis of variance. If you've kept up, as I've said, those computations are very, very much like they were for previous statistics. So hopefully the practice early on has put you in good shape for this one. This is the end of the ANOVA video series in terms of this computation, and I hope that I've benefited your experience in statistics and helped you out in making progress with this topic.